All right, I'd like to welcome everyone today for our latest presentation. This is going to be on non-contact technologies. Specifically, we're going to talk about laser technology as well as radar flow meters that you might have seen out there in the industry. These are both non-contact designs, and we'll talk about a little bit of the plus and minus of each. My name is Rick Dey, and with me is Darrell Kuta. We are in the water platform group of Teledyne, and we are business development managers. We've both been with Teledyne for quite a few years. We won't say how many, but quite a long time. So a lot of expertise, a lot of experience with flow monitoring. And so we're going to try to make this as educational, informative as we can. So for now, I'm going to turn it over to Darrell.
Thanks, Rick. So today we want to talk to you about the velocity technologies, mainly the surface and below the surface velocity sensors. We're going to go over the system installation, the safety concerns, maintenance that you may have to do with non-contact sensors. And we'll discuss the fixed and portable flow meters and loggers, different applications where you may use them. And then the impact of self-diagnostic capabilities, predicting and preventative maintenance schedules. So how you can use the diagnostics to determine when you need to go out and maintain the equipment. And from this webinar, we will have a clear understanding of both technologies and the benefits of using non-contact flow meters in open channels. So let's start. What is common among non-contact sensors? They're both used in open channels. And as you see here on the right, we can use them in round channels, or we can use in rectangular channels. The size of the pipe can vary from anywhere from 6-inch up to 20-foot wide channels, just as long as it is a open channel. So as far as with the non-contact sensors, they're mounted above the flow stream. And as you can see here, they can be mounted on a pole. You can anchor them to the wall. And with the non-contact sensors, you need to read the level to calculate the wetted area, the cross-sectional wetted area. And we're using ultrasonic sensors on both the radar and the laser non-contact sensors, and they both read the Doppler shift. So we're going to talk about the different ways they read velocity, but in the end they read a frequency shift, a Doppler shift, to determine the direction and the speed of the velocity. So why do you need a non-contact flow meter? Safety is the biggest concerns. If you can minimize the amount of times you have to have a confined space entry to send a technician down in the sewer, the much better off you're going to be, and the safer it is for your technicians. And another reason is the reduced maintenance. So if we keep a sensor out of the flow stream, we don't have to worry about sediment, debris, and other things covering your sensor. So that's going to reduce your maintenance. And what that ends up doing is reducing your operating expense based on the two things I mentioned. The fewer times you have to go down there and clean the sensor and maintain it, it's going to save you money on confined space entry, and it's going to be much safer for your technicians. So overall, this can save you thousands of dollars throughout the year. So what else sets the non-contact sensors apart? Well, the velocity technology is the main thing. So radar sensors read the surface of the velocity to calculate the average velocity. The laser reads subsurface below the surface of the water. And the level for both radar and laser use an ultrasonic sensor to read the level. And with the ultrasonic sensors, they can either have a built-in ultrasonic sensor or a remote ultrasonic sensor, depending on your application. Now, radar velocity technologies. The radar the radar units transmit a high frequency impulse signal. Once it's reflected off the surface of the water, it receives the signal as an echo. The new signals will not be transmitted before an echo is received. So it sends it out, it waits to receive it, and then it'll transmit the second one. And the sensors, they measure the surface movement of the water. So what that means is that we need some anomalies or ripples or something on the surface of the water so that it can get a reflection back into the sensor, and then it's going to read that as the Doppler shift. And so it does require that it has an agitated surface so that we can get a return signal. So here's an example of that. The radar reads the surface, so it transmits the signal, bounces off the ripples or anything in the water, and it gets a return signal. And then it uses that to calculate the average velocity. Now, in some cases, it may require that you do a flow profile to determine the coefficient to be used with that surface velocity. Now, one of the drawbacks on it is if you have slow moving water, the surface may be smooth. And so think about it, when you transmit a signal, it could reflect off the surface away from the sensor. That's why it would need some type of ripples or anomalies on top of the water to get a return signal. So as shown here, a smooth surface, when you have slow velocities, like around 1/2 foot per second, it could potentially just hit the surface, bounce away, and then end up with no velocity reading. Now the laser velocity, the way this works, it's going to take a level reading to determine the distance to the surface of the water. Then it's going to fire the laser, which can read up to 15 different points below the surface of the water. And so you can choose 1 point or up to 15 points. And what we're looking for is we're reading just below the surface of the water, subsurface of the water, to find the peak velocity. And we read the peak velocity, and then we use the coefficient 0.9 to determine what the average velocity is. And this is known as our multi-point, multi-depth velocity reading. Now for hazardous areas, both the laser and radar sensors can be purchased as standard or hazardous. So make sure you know what your ratings are for your application. So we have the standard and the IS, intrinsic safe rated. So the IS rated, the EX laser sensor is rated as class 1 div 1, and it's also rated as the IP68, which means that it can be submerged for 6 feet up to 72 hours. Now the radar sensors are rated as class 1 div 2 or zone 1, and they're also IP68 rated. So you want to make sure that you analyze your application, find out what it's rated for, and take a close look at whatever sensor you purchase to make sure that it actually does meet the specifications and the ratings for that particular application.
All right, well, thanks, Darrell. Great explanation of both those technologies. Again, pluses and minuses of really each. You have to determine what your application is, but anyway, that's kind of a quick overview of how those two work. Now I'm going to talk a little bit about some of the applications. We're going to talk about some portable loggers. So here's a good picture of what we would call a portable logger. These are IP68. They're rated for submerged. Submergence, submerged flow. So if these things go underwater, they are designed to handle that. They're typically battery powered. So you'll notice on this one here on the wall, there's 2 lantern batteries that go on those normally, and sensors down in the water, or it can be a laser and can be above the flow. For more of your permanent applications, you have to determine, do you have AC power? So a lot of cases you'll have AC power, a lot of cases you won't. So I'm working on a project right now in the Northeast where they are currently going to be running batteries, but eventually they will have AC power run to those locations. In the short term though, they can do something like this, and this one's a good shot of a deep cycle marine battery. You have the flow logger in the cabinet, and there's a solar power charger right above it. So a lot of flexibility on power options for these, whether they're permanent or portable. A lot of what you need to look at is what is your ultimate goal? Do you need a local display? If you don't, a lot of times people will just run either analog output signals to a PLC. A lot of times you could do Modbus to a PLC. In this case, they are going to go with cellular. So you have cellular modems that are transmitting the data as well. So need to determine what your ultimate goal is on the power, really, the power option. Okay, so let's look at some of the sensor mounting capabilities. There's fixed mounts. There are also adjustable mounting capabilities. So here's one that is a fixed angle bracket design. This is one that's more in the in Europe. This is one that's an adjustable mount. This is for the laser. And what you'll notice here on the wall is there's 2 bolts that hold the bracket onto the wall. It makes it easy to adjust it if you need to. That sensor will actually measure the pitch and roll of the sensor itself. So it knows the X angle and the Y angle, which is very important when you're installing. You also need that for accurate calculation of the velocity. So both of these are important factors when you're looking at installing. This sensor can be installed either pointing into the flow or pointing away from the flow. It doesn't care which direction. It's measuring an absolute velocity. It should also be noted that this sensor can measure positive or negative velocity. And one thing that's kind of good about these things as we go down the road is we're finding that you really don't need a lot of experience to install these things. Normally, with any non-contact, you're going to mount it roughly right at about the crown of the pipe. So you need to just drill a couple holes. You can put a level on there to kind of get it where you need it to be, and you tighten the bolts and away you go. So much easier than installing, in a big 84-inch pipe where you have a lot of flow and it's nearly impossible to get a mounting band or something in there. So not a lot of experience needed to be able to install one of these. Okay, so here's a radar sensor installation. In this case, there's 2 different designs here. One uses a separate ultrasonic. The other one has the combined radar ultrasonic built into it. So kind of give you an idea how some of these things can be installed. So let's look at some difficult applications. This is one that was actually Istanbul, Turkey. Very challenging location. Water is free falling into that channel. So a standard unit wasn't going to work very well because it would have tried to measure level right at that foam part, but try to measure the velocity into the channel. So that one had to be, we had to do some modifications to a unit. And what we did is we came up with a remote ultrasonic level sensor. And how that works is normally we would be reading that level in the bottom of that channel. So we would focus in the wrong spot. So what we did is we now have a version that has a remote ultrasonic sensor that mounts up into the pipe, and it will reflect off of a horizontal mounting bracket, and now it will measure level in the same location as it's measuring velocity. This does really 2 things for you. One, it allows it to adapt for these kind of horrible conditions like I just showed you. And the other one is it will read level and velocity in the same location, which is a more accurate measurement point for measuring area velocity flow. So it really helps take care of two problems. And normally though, you want to have a pipe that's going to be probably greater than 24-inch before you start putting something in like that. So it makes it a little bit challenging when you get into 8-inch pipes, 10-inch, 12, not going to be the easiest thing in the world to install. So you need to keep that in mind. Okay, here's some kind of creative mounting options that we've seen. We currently don't offer this, but we have seen it in the industry out there. And it's kind of a neat little chimney mount. So there's a bracket that goes at the lid of the manhole. It hangs down and the sensor will hang off of that. And so now you don't have to actually go in and do the install. You do need to know the depth. So you need to know the water depth flow so that you can calculate the area. So that's one area, one thing you will have to calculate. But this is kind of a creative way of doing something like this. Here's another temporary mount, and this one is more of a jack style. Looks like an old jack from a car. There are hydraulic ones out there as well, but this will crank across the manhole and hold that sensor in place. Again, the XY axis, the diagnostics that come with it, is very important in order to know that you have it installed correctly. So this is kind of give you an example of where they would do this. We see these more in like Hobos pipes and things like that, where they don't want to put screws or any kind of bolts into the manhole wall. Okay, so how do we get these things out? You know, typically you're going to require an initial manhole entry in order to mount the bracket. But once you get that bracket installed, you really shouldn't have to go in there. And one way that we get around that is with this street level installation and / removal tool. This, again, is a really, really good way of pulling the sensor out if you needed to do maintenance in that manhole, or if you needed to service the sensor for some reason, you can do that. It's about 1/8 of a turn. You just click it and it unlocks the sensor, and you can lift it right out of there. Okay, so how do we work when we go underwater? So all of these sensors typically will have occasions where they might go underwater. So what I'm going to talk about is some of the ways that you can measure. One would be a continuous wave Doppler sensor that most of you may be familiar with. And these have a sensor that's on the bottom, typically on a ring. They will measure the level of water, so they know where the water is, and then they transmit a frequency, and we calculate the Doppler shift like any other device. We got a little creative on this one when we go submerged, and I'll explain that in a minute. The sensor is going to look something like this. So when it goes underwater, it's no longer able to calculate the velocity, because where it sees the velocity really isn't moving. So what we have is a continuous wave Doppler sensor on the bottom. It's upside down now, so it's mounted on the sensor itself, and it will calculate the both level of water, so it knows the amount of submergence, so it's going to accurately tell you how deep that thing was underwater, and it's going to use continuous wave Doppler to calculate the velocity. So a pretty good option, considering when you go underwater, your hydraulics are about as bad as they're ever going to get. You have swirling, you have all kinds of nasty stuff going on. So this is a really good way to do it. So this is one way to calculate when you're underwater. Some of the other technologies out there, more of the surface guys, use an electromagnetic sensor. So what the electromagnetic sensor does, it's mounted again on the bottom of that sensor, but it's measuring a peak or a point velocity right at the actual sensor itself. So these been around for a long time, so they have a pretty good proven track record. Probably one of the disadvantages, they see right where they're at. So if you do have that sensor mounted a little bit higher, it may see some swirling and stuff like that that may not be real good velocity data. But that's how that one works. Okay, so what do we do for diagnostic? How do we predict when we need to do maintenance and scheduling and all that? Most technologies out there, again, including us, really rely a lot on the meter diagnostic. And we use that to evaluate the data. So here's one where I'm looking at a graph. I see my level, my velocity, my flow rate. Everything looks really good. No problems there. And you can actually set these to show an error. If you did get a bad reading, it would show up here. So in this, I can see I had not one single bad reading for all the data that I collected. Scatter plots, big one. People use scatter plots all over the place, and they are very useful as well. What these will tell you is a couple things. One, the repeatability of the meter and the readings that you're getting. So you should see a nice cigar pattern, which we do here. The other thing you'll see is a couple outliers. You see those up on the top. Those are probably not good readings. But you'll also can tell the hydraulics of your application. So scatter plots are used to determine surcharge, submerged events, and backwater events, and so on. So scatter plots are very useful for that purpose as well. One of the big things, and this is one that I look at all the time, is the diagnostics that we get back from a meter. In this case, this is a laser. which is what I'm obviously most familiar with. What this is telling me is the bottom pane or the bottom axis is the speed of the water. So when, in our case, when the laser takes a reading, it takes 5,000 scans in about 2 seconds. And what it's doing is every reading that reflects back, we transmit a known frequency, we get the return frequency shift. The more that agree, the bigger this signal looks, okay? So when I look at this, I see we have a frequency roughly 1.7 meg, which is about a foot, 1.7 feet per second. The more that agree, the bigger this signal is. On the left, it says FFT amplitude. You'll notice that is in the 8,000 range. We need a minimum of about 500 to consider it good. So in this case, I look at this, I have no question we are getting really good signal back. We agree on what we read. There's no doubt in my mind that this number is accurate. One thing that should be noted, especially with the laser, is that it reads the absolute velocity where it looks. And what I mean by that is if your profile, your velocity profile is shifted to the side a little bit, the water's coming around a curve, whatever, it could potentially read low if it's not seeing the peak. It's almost impossible for it to read high. And what we're learning over time now is it will read higher flow than a lot of people had anticipated. And that just is because it is actually seeing more accurately what the velocity is in that channel. So a lot of questions on some of this. And this data right here in this diagnostic is like an MRI that tells me exactly what that laser sees. Okay, what do we want to do? We want to look for the warning signs. We want to see what's happening. We want to look for deteriorating signals. We want to also look, is my data not updating? So am I not getting my data? Is it not pushing in? That could be related to cellular things. So things like that. We use historical data also to look for trends. There are more and more software packages out there. You're going to see one from us shortly that's called FlowLink Cipher. And what that is a software program that is going to help you do more predictive analysis of your site. So it's going to tell you, hey, something's a little weird here. So you'll see a lot more of that kind of software, not just from us, but from other people out there as well. Okay, one of the things we look for, signal quality, and one of them, ultrasonic, is a big one. This ultrasonic signal strength has been out for a long time, so it's not a new thing, but it's also a very important one. I had an application not too long ago where in the actual application, the signal strength was down in the 20% range, which is extremely low. Normally, you should see something in the 50 to 90% range. When they pulled the sensor, they held it by the side of the road, it was 95%. What that tells me, though, is that the hydraulics in that channel are very turbulent. So we have very choppy flow. We have waves, and it looked like a lake. It looked like a real rough lake, which means that signal is reflecting off of one of those waves and actually shooting off to the side. So this is a very useful tool to be able to tell you really what's going on. Velocity. With the standard area velocity you put on a ring, you want to know a couple things. You want to be able to know really how good is my reading. And we store things like velocity signal strength, spectrum strength, and spectrum ratio. And those all have their own functions, but when we take a reading, we turn up the gain, we get reflections back. That's called signal strength. What we get back that we use to interpret or calculate the velocity is known as spectrum strength. And that's got to be greater than 20% to consider it valid. So if my flow is very noisy, very turbulent, that'll show up in the velocity spectrum strength. And spectrum ratio is a reading that is telling you how many of the particles are coming at it. And what I mean by that is in a perfect world, your hydraulics, everything's coming straight at the sensor. That velocity spectrum ratio should be 100%. If it's not, and that'll tell you that you have something going on in that channel. You got swirling, you have a broken pipe, you have whatever. So a lot of things that you can use on a standard area velocity. In the case of laser or some of the other technologies out there, there's a value called Doppler power, which really is a measure of the quality, like I was just showing you, of the reading that we're getting back. So those are very, very beneficial to be able to determine the quality of your data. And again, evaluate your data trends. So here's one where we have signal strength. And you'll notice on an average, it is quite a ways up there, but you'll notice at the end, it dropped way down to about 5%. So something happened to that sensor. Maybe the mount came loose, maybe it surcharged, something got on it. But bottom line, somebody needs to go do something. Okay, again, use the data to evaluate scatter plots. You want to look at some other stuff too, like repeat readings. So when I look at data, I look at stuff like this. Look at your line graph. We can see we have very repeatable level velocity data. You'll notice the level looks noisy, but the velocity also looks noisy. What that tells me is there's nothing wrong with the sensor. This is telling you this is some sort of a pumped flow application. Both of these sensors are independent. So one can do one thing, but the other one should not be affected by it. When they both do this, then this is a clear indication to me that this is real. So these are good readings. We can display it in the software and tell us if it's good or bad. We have very nice repeatable diurnal pattern, and we have no repeat readings in this data. Okay. So let's look at some of the data and how we evaluate that. So when I look at data, I look at this and I go, this is really kind of a lot of flat lines in the data, okay? Why do we have flat lines in the data? Most equipment out there, if it can't get a valid reading, will repeat the last reading. And in this case, you can see from this data, we have a lot of repeat readings, okay? So when I look at the tabular data, you'll see it's 0.919 for an hour and 45 minutes. All right, so when you start looking at your data from whatever equipment you get, you really want to pay close attention to this. Any flat line is a bad sign, regardless of who's you're using. So when I look at this, this is one where, how would you defend this data? So if it did go to court, it's a billing application. There's nobody that I can think of that would be able to defend. We had the exact same reading for an hour and 45 minutes. So you need to really, really pay close attention to your data. Okay, again, scatter plots, we want to look at that. Here's a really good scatter plot. So this is what you're looking for. A couple outliers here and there, but not a big problem. Here's one that you want to be careful with. So this is what they would refer to as what's called cornrowing, kind of an interesting term. But you can see that the lines are not real. So here you have a lot of repeat readings. You have a lot of flatline stuff. This is very much, I don't know how you would use this data. So very poor data in this case. Okay, so non-contact. Typically non-contact, again, we do a velocity measurement using Doppler. Non-contact typically uses an ultrasonic level measurement. The advantages of non-contact is that they are much more accurate than level-only devices. In the old days, you used an ultrasonic to measure level and calculate a flow based on Manning formula. You got a nice pretty graph, you got a nice line, but it really didn't mean a whole lot because Manning formula is one of the least accurate ways of measuring flow. So when you use non-contact area velocity, now you have the velocity component that will make your accuracy much, much greater. Above water, we're not in the flow. So this is huge. And again, people don't want to get in there more than ever. Minimal maintenance, you shouldn't have to get in there. If you have a non-contact device, the last thing you want to have to do is go back in and work on it all the time. So non-contact will give you minimal maintenance requirements. And as Darrell said earlier, you're going to reduce site visits. You're going to reduce your operating costs. So all big things. Okay, some of the advantages of laser. So we'll just talk about laser. Laser is going to better represent the peak velocity. So with pretty much all of our technologies, we're trying to calculate the peak, and we multiply by a factor, typically 0.9, and that will get us an average velocity. The laser is the only one that will actually go subsurface to measure that peak velocity. So if your hydraulics are good, everything's moving in the right direction, pretty much any of them will work pretty well. If you have less than ideal hydraulics, I have very slow velocity, I have no surface turbulence, or I'm in an outdoor application where maybe the water on the top is getting blown by the wind one direction, but the water below it is actually going the other direction. So laser subsurface is going to have a better chance of finding that peak velocity for you. It is the only unit out there that will measure a multi-point velocity measurement. So instead of just shooting a shotgun blast at the surface, we're actually going below it and getting very, very precise readings all the way through that water to a point. It is available as an intrinsic safe or a standard. So now you can take the worry out of your hazardous location. Darrell mentioned that every manhole technically is classified class 1, div 1, not div 2. And so you have to determine, what is your risk assessment on that? Do you have to follow that? And more and more we're seeing that people are following that class 1, div 1 rule because it doesn't cost a whole lot more for the meter itself. The performance is not degraded because of that. And so you're playing it safe the whole way. A lot of flexibility in data logging now, and for both portable and permanent locations. So you need to determine, what do you have for power? What do you need? Do you need a local display? Do you need analog Modbus? Are you going to go to RTU? Are you going to go to SCADA? So you need to look at all those things, but there's a lot more flexibility with logging and meter options these days. And again, with different applications, sometimes the built-in ultrasonic will work. Sometimes you need a remote. So you have to kind of determine that depending on, again, your application. Easy programming. We want to make these things as easy as possible. And most of them are, you can program in the pipe size, you set the level, and away you go and you're done. But you really don't want to have to go in and profile. That's one thing where I know a lot of people do that. That's kind of old school stuff, and that's been done for years. Doesn't hurt. Not a bad idea, but that technology's been out since probably the late 80s. So electromagnetic point velocity is a good comfort, I guess, comfort reading, and it'll tell you, yeah, you're pretty close. But I always rely on the meter to give me the most accurate reading. Okay, so non-contact, what are some of the disadvantages? Well, if you have debris on the surface, so if you have a lot of floating stuff, and that could potentially cause you problems. Surface foam, so anytime you have a foam application, we don't recommend really ultrasonic, or in this case, probably any non-contact. What they will do is they would typically read, probably very accurate, what the foam is doing, but that doesn't necessarily relate to what is happening under the flow itself. So you need to keep that in mind. These devices are not miracle cures, so you need to have some level of comfort in what you're trying to measure. Non-uniform flow. So all of these devices are reading close to the surface. They're not going all the way through. They're not doing a complete velocity profile like an ADFM, if you're familiar with the acoustic Doppler flow meters, or pulse Doppler. So if I have a channel where I have a 4-foot weir wall at the bottom and there's 8 feet deep, it does not know that there's a 4-foot weir underneath. So we are using, again, a USGS rating, which is 0.85 to 0.95. We chose 0.9 as a coefficient, and that's going to be very close provided your flow is uniform. Okay, so keep that in mind. Again, not going to work in every application that you might have. High concentrations of steam. This kind of goes hand in hand with foam. We don't want a lot of steam, typically on any device. Radar may work a little better with steam than maybe the laser, because it doesn't, I don't think, is affected by steam quite as much. But again, in general, you want to keep away from that if you can. Limited non-obstructed space. Okay, so all of these devices typically shoot a 45-degree angle. So whether it's radar, laser, or whatever, that sensor every foot up is roughly a foot out. So you need to keep in mind the size of your manhole. If you have a limited space, you may not be able to raise it up a whole lot. You may have to be fairly close to the water. Sometimes that's fine, sometimes it's not. So you need to keep that in mind as well. All right, so we're going to go ahead and wrap this up, and we'll open it up for some questions. Non-contact area velocity is really kind of the way everybody's going. We see more and more of these. We came out with the laser 2013, but there are a lot of different devices out there that do this. Most are radar surface velocity, and again, the laser is the only one that goes below the surface. Getting into a manhole, being in a manhole environment is more of an issue, as we all know, due to the environment we're all living with. Initially, it was dangerous hydraulics. Nobody wanted to get into a pipe that's 84-inch deep, and the thing is 84-inch size pipe, and it's 3 feet deep, and the water's moving 8 feet per second. Very, very dangerous to get in there. But really now it's more of what is in the water. So some of you may have attended one we just did on COVID-19 and using samplers and things like that. So you'll see that more and more people are looking at what is in that wastewater as well. So this leads more importance to non-contact, because even if it's a small pipe, could be a 15-inch, 10-inch pipe, you still need to measure that flow, but nobody wants to get in there and be in contact with that water. So non-contact, again, is more of a big deal than ever. Non-contact area velocity is really giving you a lot of flexibility in your measurement capabilities. So when you look at some of the devices out there, we're going with more smart technology. In our case, we have the signature flow meter, and what that's going to do for you is that allows you to use whatever sensor you need for your application. So if you determine an area velocity on a ring is good enough, you can just plug that in, scan it, and it sees it. Maybe you decide this is too low a flow for that. I want to use a laser. You can plug a laser in. So you need to really look at your equipment options and the flexibility that you can have. So really, it's all about getting accurate data. We want safe environment, remote communication. That's big. And again, everybody's kind of going that route as well as we are. And so when you have remote data collection, you need to have quality data. And as long as you have that, then everybody's safe, and you're getting your job done in a good fashion. So that's where we are seeing things go. So for now, we'll go ahead and we'll open this up for some questions. And for those of you, you can go ahead and use the Zoom Q&A function as indicated on the left side there. For any additional information, we have listed both your local ISCO representative. So you can click on that and you can find out who is in your area. We have some very, very talented and experienced reps in the industry, and probably some of the best. And they can certainly come out, look at your application, and evaluate and give you their recommendations. But you can also get a hold of Darrell.Kuta@Teledyne.com, or you can contact me, rick.dye@Teledyne.com. And for that, we'll go ahead. I want to, again, thank you all for staying safe and appreciate your time today. If you have questions, feel free to reach out to us. We'll be happy to tell you what we know. And that, I'll go ahead and open it up for questions. All right. Well, thank you again. We do have a couple good questions here. One is, if I do velocity profiling and I find it to be, the meter to be off, can I adjust the coefficient to better represent what my profile says, my manual profile? And the answer is yes. And I think most technologies, whether it's laser or radar, do have that capability. By default, again, as I stated, the 0.85 to 0.95 has worked quite well. And that's a USGS thing, but it really depends on the smoothness of the pipe, the roughness coefficient and all those kind of things that go into it. But most equipment will, by default, come out with a 0.9 coefficient. And yes, you can adjust that if you need to. All right, here's another one. Can I alarm off some of the diagnostic diagnostic information. And the answer to that is yes, you can. In most cases, they will read either some sort of a signal strength or in the case of laser, Doppler power. Radar may have something like that as well. I'm not overly familiar with that, but anything the meter reads, you should be able to alarm off of it. So that's huge when you have a non-contact device and you don't want to have to get in there. Let it tell you when it needs some attention. So again, look at your application, look at the technology you chose, make sure it can do those things.
And Rick, we got another question came in about what is the minimum depth of water needed for some of these sensors? And then there was a similar question about the level readings. So as far as the ultrasonic sensors, you know, the range on most of them is 0 up to 4 foot or 10 foot. It depends on the sensor on the range, but most of them can read level down to 0. But the difference is the amount of water you need to be able to read velocity. So as far as the ISCO laser flow sensor, we can go all the way down to 1/2 inch of water depth, and the minimum velocity is at 0.5 foot per second. And now with other technologies, their range is the minimum level. Yeah, it's anywhere around an inch or so, but you need to look a little closer at the velocity. So we need to make sure that there's enough surface turbulence on there to get a return signal with a radar sensor.
And that's a good point, Darrell. And yeah, I would say we have read below our spec, which again is 1/2 foot per second, 1/2 inch deep. And we've done quite well with that. In a lot of cases, there's no other technology they can use. But one application I was involved with used a surface velocity technology, but they had a hard time getting it to read, and put the laser in, it worked, but it was reading about 2 feet per second. So I thought that was a little odd. We looked at the application and it was a wide channel. It was about 10 foot wide. And even though below the surface it was moving that fast, on the top it was like glass. So you have to keep that in mind, you know, when you look at your application. Make sure if you go the radar route, that you have enough surface turbulence to be able to read that.
Yeah, thanks, Rick. Then there's another question that came in that's along those same lines, because someone was asking about if you need to install aerators on the applications with the smooth surface, you know, to create some surface turbulence. You know, so I have seen that before on other technologies that they needed an aerator to create surface turbulence to be able to get a velocity reading. But with the laser flow sensor, no, that particular application in Canada, they were able to turn off the aeration, and then the laser was able to, you know, penetrate subsurface and read the actual velocity.
Here's one, Darrell. Can these work in poor hydraulics? And what are the upstream, downstream requirements? So yeah, that's a good question. And the answer to that is they're not miracle cures, none of these technologies. So you want to give it the best chance you can. And we see these applied in applications where they're just ridiculous. And, you know, so give it some common sense when you apply them. 5 up, 2 down diameters is a fairly normal kind of thing. And so give it the best chance you can. But as I mentioned in the presentation, if you have a weir wall downstream, it doesn't know that. So it's not going to work in some of those cases. None of these non-contact area velocities will know that. So you have to be a little careful of what you do, but make sure you give it the best upstream, downstream. And really it's all about the hydraulic profile. None of these meters do a complete profile. The laser will go below the surface, but it does not do a profile as well. So there really are not many technologies that will do a complete velocity profile. So give it the best shot you can, and you know, and you should be okay.
Right. Yeah. So the key is with any flow meter, you really need uniform flow to be able to get an accurate flow reading.
Here's one. How often should I calibrate my sensors? Good question. We get that a lot. I know a lot of times people that are using ultrasonics or bubblers over flumes, they might do a semi-annual, sometimes quarterly, or they'll go and they'll verify the level. It's a little more difficult when you're doing area velocity because with non-contact or even contact sensors, because you're actually going in, somebody's got to measure the level, and you're normally doing that with a ruler, and that's one of the more challenging things, and probably the biggest errors that we see with flow data is calibrating that level. But you go in, you can do a level measurement. In the case of the laser, we have a distance measurement, so we know where the water is. And if we do a manual calculation of the bottom of the laser to the bottom of the channel, we can subtract that distance to calculate the level. And that's one of probably the most accurate ways of doing that. Having said that, how often should you calibrate that or check it? You can store both those readings. So anywhere down the road, you can double check and make sure it hasn't drifted. Ultrasonics are pretty darn good. The only thing that would normally cause drifting would be maybe a temperature gradient, maybe steam in the channel, or if the sensor failed, it would be typically related to a temperature sensor. So anyway, it's kind of what you're looking for on that. And can we alarm off of some of these diagnostics? Again, yes, we can alarm off of anything that meter reads. Calibration of the velocity, you may go in and do a manual profile and see how that reads. I'm not a big fan of that because, again, it's the human error factor. But as just a kind of a comfort level, somebody will go into a manual profile and say, does it read close? If it does, I'm a fan of leaving the meter read what it reads, but you can take notes and log that in. So your level measurement, your velocity measurement, really that's all there is to it. So on the calibration stuff, you might require semi-annual or not even that frequent. Just depends on your own requirements.
We got another question in. Can you describe the range of surface roughness for which a radar velocity sensor will work or will not work? It's kind of hard to quantify, what the roughness would be. I would look at the ultrasonic sensor. If you look at that surface and you determine that you would not be able to use an ultrasonic sensor on there because it's too turbulent, you wouldn't be able to use the laser or radar on there. It would just be, because both sensors require getting a level reading. If it's really rough surface, chances are the flow might not be as uniform either. So it would be a difficult application. But if you've got waves that are 4 inches in height, I think you're going to struggle with trying to get a reading.
Okay, here's a question. I know that non-contact is not affected by silt or debris on the bottom, but can it compensate for the flow area calculation? If not, wouldn't the flow quantity read higher than it is? Good question. The answer to that is both yeses. We are not necessarily affected by the silt level on the bottom, but they don't know that there's silt on the bottom. And yes, you can enter a silt level factor into the meter. Typically, all of them I would think would do that. And so it's going to take that out of the cross-sectional area. If you did not, you're absolutely correct. It would read higher than what's real. So that's one of the biggest challenges that I see people faced with right now is silt level changing. The one thing you want to keep in mind is when you go non-contact, you eliminate anything in that flow. And that has had a significant impact on silt levels. So if I put any sensor in the flow, and sometimes I see people do that, they'll put an area velocity in, and then they might use a laser to measure, as a verification. And that AV sensor may or may not, but a lot of times they get covered and stuff, and then that just causes kind of a damming effect. Without having anything in the flow, then you have more of a scouring action, and you'll keep more of the debris out of the channel.
We have another question on how much does turbidity affect flow measurement? So depending on, as far as the turbidity on a radar sensor, it has no effect. because it's reading that surface of the velocity, surface velocity. You know, with the real low turbidity, you know, radar sensors will work fine with that because they're not reflecting off the particles in the water. The laser flow sensor can work in very turbid water as well. In fact, you'll get a stronger return signal with turbid water because it has more particles to reflect off of. And then on the other end, for very clear water, we've used the laser flow sensor in applications like after the UV disinfection. So it's very clear water. You know, it just has a lower Doppler signal just because it has fewer particles to reflect off of. But as far as both technologies can work with you know, essentially clearer water or very turbid water.
All right, so here's one that says, can a magnetic sensor used for surcharge measure velocity in the main line? And same question for Doppler sensor with the laser. Yes, both will read the velocity. The big difference is the electromagnetic is going to read right out where the sensor is, so it's got a fairly limited range. And as long as the water is moving in that direction evenly, then it should work fine. The continuous wave Doppler probably would have a little better chance, or we think it will, because it's transmitting away from that sensor. Both of these are normally going to be mounted at the crown of the pipe. So once they go underwater, neither the radar or the laser are going to work. So now we're going to shoot a signal into the flow, and one would be continuous wave, so it's getting 2 to 4 feet out in front of it, and the other would be electromagnetic, which is typically right at the sensor. So kind of got to keep that in mind. Again, as I mentioned, neither one of these applications, when you have a surcharge, are going to give you good hydraulics. So you're going to need to expect probably not great performance during those conditions. So here's one. We know you have modem capabilities. Can we work with other modem technologies? And the answer is yes, we can. We worked with a bunch of different ones. Telog is one of them you may have heard of. And we will normally send some sort of a Modbus signal to that device, and then it will take it, store it, and transmit it. So whether you're using an ISCO modem or you're using somebody else, most of the time we can connect to a non-ISCO modem. Obviously, we'd like you to have an ISCO modem, but certainly we can work with the other ones out there as well. Let's see, why radar cannot measure as low as laser. Is this because it's a bigger surface area and the laser is tightly focused? Not necessarily. I think the biggest difference is the radar unit has to have a reflection. So it's got to have something on the surface. And for that reason, the typical spec, and some variation to that, is below about a foot per second, 0.75 feet per second. The biggest reason I think that the laser can read that is that because of the way it scans, it takes 5,000 readings in about 2 seconds. And its signal is so clean that the signal to noise ratio is very good. And so that's what it's all about, measuring the signal from the noise. And when you have a very clean signal, you're able to read that. As that water slows down, a couple things happen. Your particles either drop out, and a lot of times what we're reflecting off of is entrained air in the water. It doesn't necessarily have to be particles. But those could settle out, and then when the water is really clean, there's less of that to even reflect off of. So the big thing is when you install something like that, you need to make sure with the diagnostics information that, yeah, we are reading, or no, we're not. And that's one thing that we can do immediately when somebody's on site. We can look and say, yep, that thing's working. Nope, you don't have it. There's no way it's going to work. So you want to make sure you do that. Here's one that said accuracy, lasers 4%. The radars are typically in the 5% range. and we are relying on, again, normal hydraulics. What I would tell you is that in a lot of tests that I've seen, we've done better than even the 4% range, but it's relying on reasonable hydraulics. So keep that in mind. I will say that I'm seeing a lot more industrial monitoring where they're using non-contact. And the reason they are is because industrial discharge a lot of times is batch. There's very minimal flow during normal times, and then they'll have a boiler blowdown, or they'll batch discharge something. And in order to capture the low end, the high end, they have to have a fairly narrow flume. If they used like a partial flume, that gets plugged up, it reads the false level, false flow. And so we're seeing more and more people now, they may use flumes, but a lot of times they're not going to use flumes. They're going to go with non-contact, put a metering manhole in there, and have good hydraulics. And if they can do that, why do a primary device? Again, 4%, 4 to 5%, which is a typical accuracy range of a primary device. Okay, I think that's about all we have. I want to, again, thank everybody for attending. A lot of really, really good questions. And if you have any additional questions or want to contact us, again, feel free to contact myself or Darrell, and we would be happy to help you out with any of your application questions or meter performance questions. So once again, thank you and stay safe, and we will talk to you at the next webinar.